We're going to get started here with our conceptual and algebraic questions for the universal gravitation problems. So for this first one, we have a situation where there is an alternate universe where Earth actually has two moons, moon A, which is a distance of r away, and moon B, which is a distance of 2r away. We know the moons are identical in mass. What we want to first do is figure out the direction of the net force on the Earth due to the two moons. So let's first think about what forces we have acting on the Earth. So if we think about the Earth here, we're going to have a force of gravity going to the left here from moon B, and a force of gravity going to the right here from moon A. Thinking about our equation, though, we know that Fg is equal to g m1 m2 over r squared. And so, since moon A is significantly closer, we're going to be dividing by a smaller value, and that means that FGA is bigger than FGB, and therefore the net force acting on this is going to be to the right. For the second question, we're told that the force that moon A exerts on the Earth is Fa, and we want to know the force for moon B in terms of Fa, the force for moon A. So this is one where we're going to set up two different situations, one the force for moon A and one the force for moon B. So in both cases, we're using this equation here. That's going to give us the force of gravity between the moon and the Earth. And so for A, that's going to be equal to g times the mass of A times the mass of the Earth all over this distance r squared. I'm also going to set one up here for B, and so I'll call that the force of B, and that's going to be equal to g times the mass of B times the mass of the Earth all over the quantity 2r squared. So that really gives us g times the mass of B times the mass of the Earth all over 4r squared. We now want to think about combining these two equations, and here's what I see. I see that the tops actually of both equations are the same because the mass of A equals the mass of B since they are identical. So we almost can get rid of that MA and that MB. And so I'm going to solve for that top part of the equation. So I'm going to say for this equation we have FA times r squared equals GM, where M is just the mass of the moons, times the mass of the Earth. And for this equation, we have FB times 4r squared is equal to GM times the mass of the Earth. So we can go ahead and set those equal to each other. So I have FA times r squared equals FB times 4r squared. The r squareds cancel out, and I find that FA divided by 4 is equal to FB. For the last part here, it says, does moon A exert a force on moon B? And the answer is yes. Both objects have mass, and so therefore they will exert gravitational forces on each other. The fact that Earth is in between them does not block gravity. You can't block gravity by putting an object in between two objects. So here we have one where we want to set up our new situation and our original situation. And in this case, we're worried about the acceleration due to gravity. So we're thinking about little g equals gm over r squared. So I'm going to start by setting up my original situation. So there's my original situation. For my new situation here, I know that the mass is going to change. We want to find the new acceleration due to gravity. So I'm going to say now we have g prime, because it's a new acceleration due to gravity. It's equal to g times 2.5 m all over r squared. Few ways of combining these to ultimately solve for this. The easiest thing, I think, is to just factor out this 2.5 here. So I'm going to do just that, and I'm going to say g prime is equal to 2.5 times gm over r squared. All right, so we just move that constant out in front. This right here happens to be our original, and so that means that for A, our new acceleration due to gravity is just going to be 2.5 g. And that makes sense because the acceleration due to gravity is directly proportional to the mass. So if the mass is 2.5 times as much, so will our acceleration due to gravity. For part B, we're now going to decrease the radius by a factor of 3, meaning it's 1/3 as big. So let's set that one up now. So I'm going to say G prime is equal to Gm over 1/3 R, that entire quantity squared. Keep in mind we do have to square that factor as well. So it's going to be G prime equals Gm over 1/9 R squared, squaring that 1/3. I'm going to make this not a double fraction by multiplying top and bottom by 9. And so what I end up getting is G prime is equal to 9 Gm over R squared. Once again, we see that this right here is our original G. So that means that G prime in this case will just be 9G. Okay, so next situation, here's one without any numbers. So we have this hypothetical planet here, Phaeton, that was located between Mars and Jupiter. And this planet has a radius of r. We're also told that an object dropped from a height of x near the surface will take a time of t to hit the ground on this planet. So based on these assumptions, we want to know the mass of it. So I'm going to work with two things here. The first is we know we're dealing with the acceleration due to gravity. So we're looking at g, little g is equal to big G times m over r squared, and we're ultimately going to be solving for this. The other thing I know here is we have some information about the object being dropped near the surface. So we're going to be thinking about our acceleration and kinematics as well. And we know that it is going to fall a distance x. It's dropped, so its initial velocity is 0, and we have a time here of t. So I'm going to work with both of these equations. The key link here, right, is that this g, all right, is going to be equal to a, that acceleration, right? G is the gravitational field, but it's also the acceleration due to gravity that we've looked at for most of the year. So work with my kinematics here. That VI term goes away using the delta x equation, and what I'm left with is x is equal to 1/2 at squared. Solving for a here is what I really want, so 2x over t squared is going to be equal to a, my acceleration due to gravity. I'm now going to take that 2x over t squared and bring it over to my equation for the acceleration due to gravity for little g. And I'm simply going to solve for m here. So I'm going to multiply both sides by r squared here and divide by big G. So I get 2x times r squared over t all over big G is equal to m. But we can really simplify that either by reducing the double fraction or just keeping in mind that anything we divide by is going to be on the bottom. So that's what we're left with, is 2x times r squared divided by g times t squared. That's what the mass of this planet would be. So we're going to move on here to some problems involving satellite motion. For this first one, we have the comet shown. We're told that it's orbiting clockwise, so something like this, from A to B to C to D and back around. And we first want to draw the direction of the acceleration at each of those points. The thing causing the acceleration is the force of gravity from the sun, so our acceleration will always be pointing towards the sun. Now, I'm not necessarily drawing these to scale. Simply drawing the direction. It obviously would be less out here at C because it's further away. For the velocity is going to be tangent to our ellipse in this case, so straight up at that point, something like that at that point. C is going to be going kind of down and to the right, and D basically directly back to the left. For part B, we're asked about whether or not the comet's speeding up, slowing down, or traveling at a constant speed at the instant shown. So A is going to be a constant speed. We see that the velocity is perpendicular to our acceleration there. So that means it's neither speeding up nor slowing down, simply turning as it revolves around the sun or orbits around the sun. At B, that is going to be a case of slowing down, and there's two reasons we know that. The first is we know that as the comet goes further away from the sun, it travels slower, and also we can just get that from looking at these vectors. That acceleration vector backwards, that velocity vector forwards, are going to lead to the comet slowing down. Same thing at C. All right, we see once again the acceleration and velocity are almost in opposite directions. It's also turning some, but definitely slowing down. And at D, we are going to be speeding up for the exact opposite reason. We see that our velocity vector is going like that, our acceleration vector is going inwards, but also in the direction of the velocity, causing it to speed up. Our next question asks about when it's moving the fastest. That's going to be here at point A. And the reason for that is because at point A we are closest to the sun. And we know that planets move fastest when they are closest to the sun or closest to that central object that they are orbiting. Question D asks when does it have the greatest acceleration? That also is at point A when it's closest to the sun, and that just really comes from the fact that gravity is the strongest at that point, and therefore the acceleration will be the greatest because it's the smallest distance, right? We're dividing by r squared, smallest distance from the sun. Moving on to this next one, we have a conceptual one about satellite motion. So this one's looking at the Earth compared to Jupiter. So the Earth obviously takes 1 year to orbit the sun. Jupiter, which is about 5 times as far away, takes 11.9 years to orbit. Jupiter also has about 300 times the mass that Earth has. So the question is, if the Earth was the same distance from the sun as Jupiter, how would that affect its period? So would we take longer than Jupiter, the same amount of time as Jupiter, or less time than Jupiter to orbit? And so the answer here is it would end up taking the same amount of time. And the reason is due to Kepler's third law. Kepler's third law tells us that as the orbital radius increases, so does the period. More specifically, the period squared is proportional to the radius cubed. And so all that matters is how far away the object is. All right, the mass of the object in orbit doesn't actually affect the time it takes to orbit. The only mass that matters is the mass of the central object, which in this case would be the sun. And since it's the same in both cases, if Earth was at the same distance away as Jupiter, it would take the same time to orbit. For the second question, we're looking at how changing the mass of the sun, the central object in this case, would affect the period of orbit for Earth while it's at its current location. And so if we increase the mass of the sun, what that's going to do is that's going to decrease the period of orbit. There are two ways of thinking about this. The one is we can think about Kepler's third law and think about how the period, specifically the period squared, is inversely proportional to the mass. So if we increase mass, that's going to decrease the period. The other way we could think about explaining this is that if the mass of the sun increases, that means we're going to have a greater pull from the sun, a greater inward acceleration, and therefore the Earth will have to be moving at a faster speed. Okay, thinking about the fact that centripetal acceleration is v squared over r, the Earth will have to be moving at a faster speed in order to maintain its orbit. So our next question here is about the two moons of Mars, Phobos and Deimos. And Deimos has an orbital radius that's 2.5 times larger than that of Phobos. And so for the first question, we're told that the orbital period for Phobos is t, and we want to find the orbital period for Deimos in terms of t. So a lot of times we would set up two equations for this one to compare the two. However, we are in luck here. With the ratio version, is what I call it, of Kepler's third law, we can just go ahead and compare these two objects that are orbiting the same thing. So we can use this version of Kepler's third law whenever we're comparing two objects that are orbiting the same central object. And so I'm going to start with that version of Kepler's third law here for A. I'm going to say that TA and RA are going to be for Phobos, so I'll say that it has an orbital period of t, and its radius, I'm just going to say, is r cubed. We're looking for the orbital period of Deimos, so I'll call that td squared, and its radius is going to be 2.5 times larger, so 2.5 r, and that entire quantity there is going to be cubed. So I can go ahead and simplify that bottom of the one side, and so I have t squared over r cubed equals td squared over 15.625 r cubed. I have an r cubed on the bottom on both sides, so that will we're actually multiplying that out. And then I'm going to multiply by this 15.625, and so I get 15.625 t squared equals td squared. So when I take the square root of both sides in order to solve for TD, I find that TD is going to be equal to 3.95 t. So its period of orbit is going to be 3.95 times longer than Phobos. Moving on to part B, we're now told that the velocity of Phobos as it goes around in a circle is v, and we want to find an expression for the velocity of Deimos. So this is one where we're going to set up two equations, one for Phobos, one for Deimos, and in both cases we're thinking about v equals 2 pi r over t, okay, the velocity of an object moving in a circle. Again, we've talked about this before. Even if it's not a perfectly circular orbit, we can still use this equation with the average radius of the orbit to solve for the average velocity. So that is our first equation, and then for Deimos, I'm going to say Vd, the velocity of Deimos, is going to be 2 pi times 2.5 r, all right, instead of r, and our period is going to be 3.95 t, what we just found in part A. So now it's a matter of just combining these two equations. So what I'm probably going to do is I'm going to take these two numbers here, the 2.5 and the 3.95, and I'm going to pull those out of this equation. Okay, I think that's the simplest way of doing this here. So I'm going to say 2.5 over 3.95, just removing those constants, times 2 pi r over t, and that's okay to do. We haven't actually changed anything, just the arrangement of them. And that 2 pi r over t is what our initial equation was over here. So we can just substitute that in. So the velocity for Deimos is going to be 2.5 divided by 3.95 times v, the velocity for Phobos. And when I go ahead and plug those numbers in, I just get that it's 0.63 v when I get that decimal. Moving on to part C, we now want to compare the acceleration of Phobos as it orbits to the acceleration of Deimos. So there's actually two ways of doing this. One, we can think about the fact that acceleration when something's going in a circle is v squared over r. So that is one option. The other one that you could also think about is g equals gm over r squared. And the reason for that is the reason why these planets are orbiting is just due to gravity. That is the force that makes these planets orbit. So we could do it either way. I'll start by setting it up with circular motion. So for Phobos, I'm just going to say my acceleration is v squared over r. For Deimos, I'm going to say the acceleration of Deimos, AD, is going to be equal to 0.63 v, which is what I just found in the last part. That entire quantity squared over 2.5 r. When I do a little simplifying here, I get that AD is equal to 0.63 squared, which is 0.3969 times v squared all over 2.5 r. I can do the same thing I did the last part, and I can pull out those two constants. And I know that what remains is just going to be this v squared over r, which is equal to a, the acceleration of Phobos. And so I end up getting that the acceleration of Deimos is 0.16 a. So that's one way of going about and doing this problem. I could, though, like I said before, also use little g, the acceleration due to gravity, because whenever an object's in orbit, it is in free fall. Gravity is the only force keeping it moving in a circle, and so its acceleration would be the same as the acceleration due to gravity at that point. So if I want to use this equation instead, I would say for Phobos, the acceleration would just be gm over r squared, and for Deimos, which has a radius that's 2.5 times as much, we could say its acceleration is going to be gm over 2.5 r squared. The masses are the same here because in both cases the mass that we're worried about is the mass of Mars, not the mass of either one of the moons. It's the mass of that central object, the thing causing the acceleration due to gravity. So what I could do here is I could pull out my constant once again. So the acceleration for Deimos is going to be 1 over 2.5 squared, which is 6.25, times gm over r squared. Remember, we're always having to square that coefficient in front of our number, and we see that gm over r squared is just equal to a, and so we can say that the acceleration is going to be 1 over 6.25 times a, which gives us an acceleration here of 0.16 if we get the decimal times a.